Here's another question on electromagnetism. And in this case, we're looking at a conductor falling through a magnetic field, and it's also connected to a capacitor. And we'll see what we have to find and how we're going to do it. So let's first read the question and try to understand it. We're being given that we have a conductor PQ, which has a mass M, and it's always in this horizontal position, and it's between two vertical rails called A, B, and CD. And there's a magnetic field B, which is always pointing into the screen. Now, we're being told that this rod is being released at the initial time t0 equals to 0, and it's always going to be in contact with the rails. And what we have to find is the charge on this capacitor as a function of time. So how will that capacitor charge? Why will it charge? So we'll try to answer those questions as well. So let's try to understand what happens. As this conductor, this rod, starts falling, it will gain a certain amount of velocity. Okay? So it will have a velocity v pointing downwards like this. So this is also going to be the velocity of the electrons on the rod. And we know that there's a magnetic field which is pointing into the screen. So this will generate our Lorentz force, which which has this formula. So that force is perpendicular both to the velocity as well as the magnetic field. And if we use either the right hand rule or the corkscrew rule, we can actually find out what the direction of this force is, right? So I guess one way to do it, if we look at things from this Q end, right, we're going to see the conductor like this. We're going to see if the conductor is cylindrical, and we have the velocity pointing downwards. So I'm just doing this in order to put both v and b vectors in the same plane, right? And then b is acting this way. So in this case, what we will end up with is a force, an FL force, that will point out of the screen like this. And this is going to be the force acting on the positive charges. So it's going to act like this from this perspective. Okay, so you're going to have a bunch of positive charges here, and the negative charges will be on this end. So the electrons are going to accumulate on one end, and on the other end there will be a deficit of electrons. So that, and the fact that this is connected to this circuit, will create a current. So it will create a current this way. And because the positive charges will start traveling through the circuit, they will end up on the plates of the capacitor, but the capacitor doesn't really let the current go through. So there will be an accumulation of charges, of positive charges on this side, and the negative charges will be on this side. And then the charge of the capacitor is given by the usual formula, which is Q equals C, which is the capacitance, multiplied by U, which is the potential difference. And we have to use that to figure out how that amount of charge changes with time. So the first thing I would do is I would look at the induced EMF, right? Because there is an induced EMF, and the reason for that is because the magnetic flux is changing. So the value for that, the magnitude, is given by the change in magnetic flux with respect to time, and that will be d over dt of the magnetic flux, which is B, multiplied by the area. So what I'll do is I'll look at the magnetic flux through this rectangular section, because that's the loop created by our conductor PQ. So we have B, and then we have the area, which is the area of a rectangle. So that's, I think, L is the horizontal distance, and then multiplied by Y, which is the vertical distance. Now this area is getting bigger with time. So when we differentiate, we have B and L outside, and then we differentiate Y with respect to time, and this gives us BL, and the rate of change of Y is just V, where V is the instantaneous velocity of this conductor at any given point. Now, keep in mind that V doesn't necessarily have to be a constant. So in this case, it's most likely not even constant, but we don't really have to worry about it too much, okay? As you'll see in a bit. So this is the EMF, which is induced. And the other thing to keep in mind is that there will be a force acting on this conductor PQ, because if you think about it, this conductor will now have a current through it, like this, and there will be a force acting on this conductor given by this formula I multiplied by the cross product between L and B, where L is a vector which has the same magnitude as the length of the conductor, and the direction is the direction of I, of the current, right? And then we said that B is pointing like this into the screen. So the effect of this will be that this will generate a force on the conductor, and that force will be pointing upwards. Again, you can try to find this out yourself using the right hand rule or the quartz rule, whichever rule you're comfortable with. So this will create a force on the conductor like this, which is B times I times L. So if we draw the free body diagram of the conductor, there are actually two forces acting on it. One of them is the weight, and the other one is the force that's trying to stop it from falling, which is BIL. So we can write Newton's second law, which is mass times acceleration is mg minus BIL, and we can divide everything by m, and we have that the acceleration is g minus BIL divided by m. So that's one thing that we're going to have to use. Now, the other thing is that the potential difference between the plates of the capacitor is actually going to be the same as the EMF, because the question says that there's no resistance anywhere in the circuit, which means that the potential difference will be the same. So all the EMF will go into the potential difference uh, across the capacitor. So we have the EMF right here. So let's call this equation 1. And then equation 2 will be the fact that our U is going to be the same as the EMF, which is the same as B times L times V. And finally, we know the fact that Q, which is the charge, is going to be equal to C multiplied by U, which is actually C multiplied by B times L times V. So now we're trying to put everything together, but keep in mind that we don't really know anything about the current, except the fact that the current is the change in Q over time. Okay, so hopefully with this in mind, we can find something useful that's going to help us determine how the change in, or how the charge changes in time. So here's what I would do. I would first write that Q is C times B times L times V. And then I would differentiate both sides. So I just wrote this here. And I would differentiate both sides with respect to time. And this is C, B, and L are constant. And then this is dV over dt. and of course dv over dt is the acceleration. Okay, and dq over dt, this is the current. So I would take this and I would put it in this equation, which is Newton's law of motion. So I have that the acceleration is equal to g minus, and then I have, I'll write BL over m first. So I have BL over m multiplied by the current, which is CBL times A. And then what we can do with this is we can rearrange it so that I have acceleration, and then 1 plus b squared L squared C over m is equal to g. So I'm just rearranging it by moving this to the other side and then doing some factorization. So therefore we have that the acceleration will be equal to g multiplied by m over m plus b squared L squared times the capacitance. And the final thing to keep in mind is that we've got our charge that's equal to CBL times V. Now, we can actually get V quite easily because the acceleration is dV by dt. So dV by dt is g times m over m plus b squared L squared C. And then the velocity is therefore mg over m plus b squared L squared C times t. So this whole thing is a constant, so it's relatively easy to integrate, and also there is no, well, we know the initial condition, which is that at time equals 0, the velocity is 0, which means the constant of integration just vanishes. So our charge with respect to time, our q as a function of t, will be equal to CBL multiplied by V. So that would be CBL multiplied by V, which we just got, which is mg over m plus b squared L squared C times t. We can tidy this up a bit, and we'll get the fact that the charge with respect to time is B times L times C times mg. I'll put the time afterwards, plus b squared L squared C t. So there are a lot of variables in this question. Well, not variables, there are a lot of variable names, I guess. There's B, L, C, and there's M, and then there's time. But essentially, in the end, if you think about it, we got a very simple expression which relates charge to time, because this whole thing is just a constant. So just a bunch of numbers, and then this tells us that the charge on the capacitor is a linear function of time. So if you were to plot it like this, so if this is time and if this is the charge on the capacitor, you'll have a dependency which looks like this. So it's just a linear increase, and the slope of this line is whatever I circled here. And that's the other question.